Okay, the next part we want to discuss the standardization. So, well, remember when we are doing the k-nearest neighbor, we are always relying on some kind of distance matrix. Well, for example, like Euclidean distance, right? And if we are just dealing with the x1, x and y coordinates, and probably we don't have to worry about the scales of the x and y axis. Well, but if we are considering some additional features we want to have, and for feature 1, the range is from 0 to 1. For feature 2, the range is from 0 to 100. And then, if we want to calculate the distances between samples using those two features, feature 1, the range is 0 to 1, feature 2, the range is from 0 to 100. So in this case, can you imagine what is going to happen? So the largest difference possible on feature 1 is just between 0 and 1, which is 1. However, the largest distance possible on feature 2 is from 0 to 100, that is 100. So you may see the feature 2 is gonna dominate the distances of all the possible samples, and this will introduce a problem. We don't want to have that. We want all the features to be treated equally when we want to before we start to calculate the distances. So there's one extra work we have to do. So I'm using the same example here, and you should have already seen this code. And I'm doing this step. So from scikit-learn pre-processing, I'm importing a standard scalar. So this standard scalar will help us to standard scale all the features. And then the first thing, I use the standard scalar and then parentheses to build a scalar. So what is that? That is a call of constructor, right? Because the standard scalar is a class name, and I'm calling this to make a constructor so that I have an instance. And the next part, I do scalar.fit, and then the data frame drop the target class. So remember, we are trying to transform all the features applying the standard scaling. However, for the target column, we want to classify, we don't want to touch that. So first I drop the target column, and then I'm doing a standard scaling. Okay, so this part is cool, but I want to use the features have already been standard scaled. So actually I have to do this. I have to give that a new name. I have to call scalar.transform and then transform everything into a new feature space. So I'm calling that scaled features. So after transforming all the features into standard scaled features, now I'm gonna use this scaled features to build my machine learning model, and this is always a safe way. Well, I'm not saying for all the machine learning models you have to apply the standard scalar, but if your machine learning model is using any of the possible distance matrix, you have to do this part. So after that, I'm gonna put the scaled features back into a data frame again. So this is the scaled features. It is a 2D array. We don't want to have a 2D array. We want to put it back into Panda data frame, so it is easier to see. So I'm putting that back into a pandas data frame, and then I'm using all the columns names, but I'm dropping the last one. I'm dropping the last one because the last column name is target class, and we don't have that. So I'm dropping the last column here. Okay, so this is the features with standard scaling already applied. So the next part, I do the same thing, splitting the training and testing data set, and I'm building another k-nearest neighbor model, and the n neighbor is 1, so that is 1 nearest neighbor. So eventually, I want to evaluate the performance of my machine learning model. So before we move on, here's another question. So how do you break up a tie? So just now, I did 1 nearest neighbor, and in this case, we won't have a tie, right? But how about we do 2 nearest neighbor? If we are doing 2 nearest neighbor, and if one of my neighbors says A and another of my closest neighbors says B, and how do we label the sample? This is a problem. So in scikit-learn, there is a hyperparameter called weight. So this weight will tell the k-nearest neighbor how do you weight all the nearest neighbors. So just now, we are assuming that those 2 neighbors, they have the same weight, but it may not really be the case. So let's say, let me create a new one. Oh, let me just draw it here. Say if I have, this is the sample we want to predict, and we have this one, this is the neighbor 1, and we have this one, this is the neighbor 2. So if we are doing the 2 nearest neighbor, and my 2 nearest neighbors are n1 and n2, okay, so in this case, say my n1 suggests that is a yes, but for n2 suggests a no. So who should I listen to? Well, the answer can be, it depends on the distance between each of the neighbor to the sample we are trying to predict. So in this case, we have the distance 1 and the distance 2. And you can see the distance 1 is smaller. So if we specify for the smaller distances, it automatically has more weight, a higher weight, and then we can break the tie. Even though the n1 and n2, one says yes, one says no, but if we are considering the smaller distance to have a higher weight, and then the tie is broken, right? So you may ask, how do we do that? How do we do that with the scikit-learn? And the answer is, well, you need to use a hyperparameter called weight. So the weight is a hyperparameter you can do when you create a k-nearest neighbor, and then you can specify the weight to be the distance, and then you can safely do 2 nearest neighbor, 4 nearest neighbor, and without worrying about the ties. Okay, so the next part. Well, how about the categorical features? And the categorical features could be a column like color. Like for this column, we have red, yellow, green, yellow. Okay, so in this way, how do we calculate the distance between a red and a yellow? This can be hard. So for example, if we have a data frame like this part, like this one on the left side, so if we have red, green, and blue, this will give us some problem, because if you see the second feature, price, and they are all numerical values, and for the numerical values, and then we can calculate the distance between them, no matter I'm using Euclidean distance or something else. But for the color, how do we do that? Well, in this case, we have to apply a one-hot encoding. So we have to transform this color column to be something like the right side. So we create a new feature called red, another feature called yellow, another feature called green, and they are all binary features. The only allowed value will be 0 and 1. Okay, and then we can actually drop the color column. So if we want to do this part, what we want to do will be, So, oops, we want to have a new feature called red and another new feature called green, another new feature called blue. Okay. So for this one, this red is a 1 and green is a 0, the blue is a 0. And for this one, it is 0, 1, and 0. And the last one is 0, 0, and 1. Okay, so after that, we have transformed the color column into 3 additional columns. So eventually, we don't have to worry about this categorical feature anymore. Okay, so another thing is, when you have transformed this data frame, you see for the price, well, the possible values could be from 0 to 10,000, for example. And for the RGB, the red, green, and blue, they can only be zeros and ones. When you see a data set like this, what are you going to do? Right, you have to apply standard scalar for sure. Okay, the next part. If we assume there are only 3 colors possible, if one sample doesn't have the color of red, it doesn't have green, and then what? The blue is the only possible choice, right? So this means if we take the red and green, if we take those 2 features, and those 2 features can predict the other feature, which is blue. In this case, we will say, okay, this B is not really necessary because using the red and green, we can predict the blue. So blue is kind of a redundant feature. So we can always drop that one. So eventually, we will have a data set like this. This will be our final data set. We only have the price and then the R and G. And this will be the final data set. Okay, so this is long enough, and I will see you in the next video.